concepts and instruments useful for studying a geomagnetic storm, and to study in particular the reaction of the ionosphere on a geomagnetic storm. So we will have a brief recap about the concept we defined in the last 2 days about the geospace, the sun, the geospace, and the ionosphere. Then we will analyze in details some papers, scientific, in 2015, March 2015. And at the end of the slide, at the end of the lesson, we will see how to retrieve, how to download data from the databases that are available all over the world in order to collect the data, to study a geomagnetic storm, and to interpret the data in order to define the ionospheric response to a geomagnetic storm. So all the stuff we treated in this course start from the sun. So just to recap, which are the phenomena that are important from an ionospheric point of view generated from the sun. Here in this slide, you can see the 3 main phenomena that determine an energy and particles flowing from the sun down to the Earth, to the magnetosphere, and then the Earth, the ionosphere, that are the flares. That is basically electromagnetic phenomenon. Okay, not only, we have also some very energetic particles traveling at a very high velocity, almost the light velocity. But in particular, the flare and the ionospheric response to the flare are related to the electromagnetic waves, very high energetic electromagnetic waves that are in the UV and X-rays frequency range. So this kind of phenomenon interact directly to the ionosphere without involving, as the other 2 do, the coupling between solar wind, magnetosphere, and the ionosphere. So the radiation reached directly the ionosphere, inducing an additional ionization in the ionosphere with respect to the background. So we will see at the end a very brief example of the flare happening in September 2017, if I remember well, with a global TC view of the reaction to this very important flare. So the effect from the sun down to the Earth is related to the speed of the light. So as you already know, the light spent about 8 minutes to reach the Earth, starting from the sun. So the flare, the effect of the flare, it's almost immediate. So the flare spent 8 minutes from the sun down to the ionosphere. Moving to the other 2 effects that are instead related to the solar wind, magnetosphere, ionosphere coupling, we have the coronal mass ejection that are basically emission of charged particles from the sun corona that can affect the interplanetary, that can transport the interplanetary magnetic field, so interact with the magnetosphere, and at the end with the ionosphere. And as Lucilla said, maybe the very first day, these particles can travel at a velocity from let's say 400 kilometers per second up to 1000 kilometers per second. So the time that the particles spend to reach the Earth, starting from the sun, is from 1 to 3 days. And then we have the coronal holes that are an anomaly, let's say, in the sun magnetic field that produce the release of the fast protons and alpha particles that again affect the solar wind, magnetosphere, ionosphere coupling, and being very fast particles, they can reach the Earth in a time that varies from a few minutes to a few hours. So for what concerns the lesson today, we will concentrate on the effect of the coronal mass ejection on the ionosphere, but just because this is, let's say, the most complex phenomenon that can affect the ionospheric behavior. Just to recap, the solar wind is a particle flow coming from the sun towards the Earth, and the solar wind is responsible for the transport of the interplanetary magnetic field. So the magnetic field on the sun through the interplanetary space, and it's the one that interact with the magnetosphere, creating the condition for the injection of particles and energy into the ionosphere. So it's the responsible basically for the geomagnetic storm. The solar wind, as you can see here, the main parameters of the solar wind is the ones we can consider to study the impact of the solar wind, is the velocity, the density and pressure, and the temperature. The velocity, as I said, is from 400 kilometers per second up to 800 kilometers per second, when the velocity is a very fast one. And so basically during a coronal hole or a coronal mass ejection events. But in a quiet condition, it is slightly slower. So the velocity is about 200, 300 kilometers per second. The interplanetary magnetic field is the one frozen into the solar wind. So it's the sun magnetic field that is transported through the interplanetary space through the solar wind. And we can, as we know, the interplanetary magnetic field travel like a spiral. So the ballerina skirts, maybe you remember that. And on the image on the top right, you can see the quiet solar wind traveling in this spiral behavior, so the green and blue lines. And at a certain point, you can see the release of a huge CME toward the Earth. So we can define a reference system for the solar wind, for the interplanetary magnetic field, sorry, including the x-axis on the direction of the sun to the Earth, and the z-axis, that is the vertical component of the interplanetary magnetic field. That is, as we saw in the last days, the quite crucial component of the IMF for what concerns the interaction with the magnetosphere. So to recall some way in which the solar wind magnetosphere ionosphere interaction can be performed, we have here some example, just few examples. That is the particle precipitation at auroral latitudes. We have seen that we have these field line currents that are able to inject directly particles into the ionosphere, into the polar ionosphere. The modification of the ionospheric current at high latitude, so the auroral electrojet, again, the field line current can induce this this cell of convection of the plasma at high latitude, creating what we call the auroral electrojet. The modification of the ionospheric current system at low latitude, so the ring current, the interaction between the solar wind and the magnetosphere, reducing the intensity of the magnetic field at low latitude, and we can see in a while the indices related to this phenomena. The ionospheric heating, we didn't spend so much word about the ionospheric heating, but this is a very important phenomenon related to the injection of energy at high latitude again, that is able to modify the dynamics of the neutral atmosphere and to create the condition for the propagation of what we call the large-scale TID, so the large-scale traveling ionospheric disturbances traveling from the high latitude down to the equator, involving, in most of the cases, all the globe. So that are these are basically a global phenomena, starting from the injection of energy at high latitude and traveling down to the equator. We have the movement, the displacement of the boundaries of the auroral oval, as Marco Guerra was saying during the first day. So during a geomagnetic storm, we have the interaction between the solar wind and magnetosphere can modify the morphology of the magnetic magnetosphere, leading to a equatorward movement of the boundaries of the auroral oval. And then we have these traveling ionospheric disturbances. That is a very important topic for what concerns the disturbances in the ionosphere that can induce a lot of effects on positioning and blah, blah, blah. And again, the changes in the polar cap circulation, so the auroral electrojet and the movement of the plasma inside the polar cap. These are only few examples on how the solar wind magnetosphere ionosphere, the solar wind and magnetosphere interact with the ionosphere, modifying its behavior. So how to measure the solar wind and IMF? We have these satellites in orbit at L1 Lagrangian point. That is the point in which the gravitational potential is quite low, almost zero. So the satellite can stay stable in this point that is always in the direction from the sun to the earth. So we are constantly looking at the sun from an earth point of view. And with the measurements from these satellites, we are able to define different parameters. So the total intensity of the interplanetary magnetic field, its X, Y, and Z components, and the parameters related to the solar wind, that are the velocity, density, temperature, and pressure. How to define the geomagnetic activity? So how to realize if a geomagnetic storm is ongoing? We defined the mainly three different geomagnetic indices related to different ionospheric region. So at high latitude, we have this AE basically, and the others in this index that is able to give us an idea on how the auroral electrojet has been modified by the geomagnetic storm. At mid-latitude, so subauroral latitude, we have the KP index, that is a global index, giving us the possibility to quantify the modification of the horizontal component of the magnetic field at mid-latitude on a global, at a global level, induced by the geomagnetic storm. And the third one is related to the low-latitude ionosphere and related to the modification of the ring currents there, induced by the interaction of the solar wind with the magnetosphere. That is the DST index. That are that is basically a measure of the ring currents and on the degrees of the ring currents, in particular induced by a geomagnetic storm. So here you have a sketch in which you can catch which magnetic station are used for calculate these indices. Then we can move to the ionosphere. That is our objective. That is just to recall the concept introduced yesterday. That is the upper part of the atmosphere in which the free electron are able to modify the propagation of the radio waves passing through the ionosphere. And we have seen that we have a lot of variability of the ionosphere, both regular variation and irregular variation. The regular variation are basically related to the day and night variation, seasonal variation, latitude variation, and so on and so forth. The irregular variation are induced by the storms, and so basically by the space weather events, but also by the interaction with the lower atmosphere, lithosphere, and anthropogenic activity. So how to study the ionosphere? We saw yesterday basically two ways to investigate the ionosphere. That are the HF sounding, that is basically realized with a radar that is able to shoot different frequency up to the ionosphere, listening to the echo back from the ionosphere. The results of these measurements are the so-called ionograms that you can see here in this sketch. By looking at this ionogram, we are able to retrieve some fundamental parameters able to define the different layer of the ionosphere. So basically the critical frequencies of the layers of the ionosphere and the related altitude. So virtual height that we can convert in physical height by using profiler and automatic scaling of the ionograms. The other way we sought to investigate the ionosphere is the use of the GNSS signals that are the signals coming from different constellations orbiting, flying at 22,000 kilometers above the Earth's surface. That are the GPS, GLONASS, Galileo, and Beidou, the most important ones. And with the GNSS signal that is able to pass through the ionosphere, reaching the Earth's surface and to be received by the GNSS receiver at ground, we are able to estimate what we call the total electron content. By looking at two different frequencies of the GNSS signals, we can combine them in order to obtain the total electron content in the ionosphere, that is measured in TeC units, that are the 10 to 16 electrons per meter square. To obtain something that is not related to the geometry of the observation, so to the angle, elevation angle with which the receiver can catch the GNSS signal, we can verticalize the total electron content values by applying a mapping function that is related to the elevation of the measurements. This is a new parameter that is very useful to investigate the irregularities in the ionosphere. That is the rate of change of TeC. So basically, you can imagine you have a receiver at ground and a satellite orbiting, and the receiver is looking at the satellites by receiving the signal from these satellites, and you have measurements every now and then. I mean, let's say every seconds we have a measurements. So if we look to these measurements all over an arc of observation, so the satellites is flying, describe an arc. So the measurements along this arc can be we can make a difference among one measurements and the previous one. So by looking at the TeC at a given time and the difference with the TeC at a previous time step related to the same satellite, for sure, we can define this rate of change of TeC. That is a very useful parameter, as we can see, that give us the idea about how the ionosphere is changing in space and in time, because we are looking at different time, but the satellite is moving, so we are looking at different points of the ionosphere. So this is a kind of merge of temporal and spatial derivative of the TeC. Then another way to exploit the GNSS signals is the measures of the scintillation that are the effect induced on the GNSS signals by the small-scale irregularities. So we can define two different indices, one related to the phase of the signal and one related to the amplitude of the signal. So sigma phi and S4, that are basically the standard deviation of the signal in the case of the phase, so sigma phi is the trended signal. In the case of the amplitude, is the standard deviation of the signal normalized to the mean of the amplitude of the signal. And in the plot here, you can see some, let's say, scintillation detected by one of our receiver. To measure this kind of scintillation, we need a particular GNSS receiver that is able to catch the signal at least 50 Hertz. We need a receiver that are a very low noise on the phase measurements, so a receiver that costs a lot, basically, about 15,000 euros, so something like this. And instead, let's say normal geodetic receiver, professional one, it could be something like 2,000. So the difference is huge. So in case, this is why we have a very few scintillation receiver all over the world, but a lot of geodetic receiver, thousands, tens of thousands receiver all over the world. So we can try to exploit the signals from the geodetic receiver by defining what we call the proxy scintillation indices. So something that is not directly the measurements of the scintillation indices, because we don't have the 50 years measurements, but we can define some proxy indices that is able to give us an idea about the possible scintillation scenario. So we can define this rate of change of TC index, that is again the standard deviation of the rate of change of TC calculated usually over 5 minutes. So with these indices, we are able to catch if the ionosphere is if in the ionosphere we have some kind of irregularities. So this is a list of references you can use to have a deeper look on the especially GNSS measurements, geomagnetic indices, and scintillation stuff. Questions?
Yeah. So the first one is of these three phenomena that I guess were the solar flares, coronal nodes, and CMEs, which are the most repeated?
I always reply to the questions you are saying in these days, it depends. I mean, unfortunately, we have not a pattern in the occurrence of this phenomenon. This is why we are not able to forecast this phenomenon. So we have not a, okay, we have some statistics on this kind of phenomenon, and they are related basically to the phase of the solar cycle. As we saw during the first day, the solar activity show a regular variation with a cycle of 11 years, actually 22 years, but this is another story. So what we can say is that during the solar minima, we expect more coronal holes than CME, for example, and this is the opposite during the solar maximum. So it depends on the solar cycle phase. For what concerns the solar flare, they are completely unpredictable. So they are, let's say, uniform distributed all over the solar cycle phases.
Second question, why do solar coronal nodes intensify the solar wind?
This is related to the magnetic activity of the sun. Actually, I'm not an expert on the sun magnetic field behavior, so I cannot give you an accurate answer, but I can study a bit and then be back to you. But basically, it's related to the fact that the particles that are leaving the sun are accelerated by the magnetic field of the sun. This is the same for the CME. So when you have a modification in the magnetic field of the sun, and the particles of the sun, the charged particles interact with this magnetic field, can be accelerated. So the solar wind velocity will be higher than the quiet baseline. This is more or less the phenomenon.
And that is the question, the last one for the ionospheric physicist. Once this phenomenon reaches the Earth, what's the response time of the ionosphere and how long does the perturbation last? That's the question.
Okay, I can, we can say that we are exactly working to give an answer to this question. I mean, almost all the ionospheric research is toward the understanding of the ionospheric response to the geospace perturbation. So geomagnetic storm, solar wind perturbation, and so on and so forth. The answer is we don't know yet, because the response of the ionosphere, as we can see during the next hour, is very variable. So you can have a sudden response to the ionosphere due to some phenomenon that is, for example, the prone-penetrating electric field, and a delayed response of the ionosphere. The reaction can last for few tens of minutes, as in the case of the flares, but can stand for days, as in the case of a CME, of a huge geomagnetic storm. So the answer to this question is, this time we don't know yet.
Other comments or questions? They are thanking you. Okay.
Thank you to you. Sorry for being so, to reply to this question. I don't know. We don't know yet. It depends. But it's like research is like this.
So maybe going into an example, we can give a bite, Claudio, of how difficult it is to study the response of the ionosphere to the attendees. So we have decided to give you a description on how to face the study of a storm, looking at one very famous storm in our community, of course. Is a storm that happened on the 17th of March 2015, and for this reason was called the St. Patrick's Day storm, to celebrate the Irish celebration. And that storm was the most studied storm during the solar cycle 24. The solar cycle 24 is the one that is just over. We are at the beginning of the solar cycle 25. And on this storm, there were hundreds of scientific papers published. So from these papers, we are picking some of the results to discuss with you how to face the study of a storm. So first of all, the approach is to look at the source of the perturbation. As we have seen from the very first day, the perturbation source is the sun, and we are lucky enough to rely on satellite observations. Unfortunately, they are not so close to the sun, but for instance, here we are seeing a couple of pictures taken by the coronagraph on board of the SO spacecraft. We have seen the SO spacecraft the very first day, and again a few minutes ago with Claudio in the recap. The coronagraph is an instrument capable with a target that essentially hides the the solar disk to observe the emission of the corona in the surrounding area. And I remind you again that SOL is in the L1 Lagrangian position, so it's capable to see anytime what happened between the sun and the earth, because it is on the direction from the sun to the earth. Of the solar disk on the 15th of March at 1:48 universal time. The average speed of the CME in the other coronagraph field of view was almost 700 kilometers per second. This perturbation took more than 2 days to reach the Earth. And also this traveling time is very variable, time by time. In this case, more than 2 days were taken to reach the Earth. And looking at this very famous paper published by Astafieva and colleagues on 2015, we can have a general description of the storm. So let me use the pointer to help you to follow all the description. So in this stack plot, you are seeing the velocity of the solar wind, the Bx, Bz of the interplanetary magnetic field, that I remind you is the solar magnetic field that we associate to the bulk of the magnetic field happening in our system. This PCC, I don't remember, Claudio, what is it? PCC?
Is it's a polar cap
in the index. Okay. Yeah. And this CMH, if you remember, is the we can consider the same as the DST index. In this first description of the stack plot, we can see, I lost the point. We can see the time in which we have the sudden storm commencement, that maybe you remember from the description that Claudio gave the very first day. You can identify it as an enhancement of the horizontal component of the geomagnetic field, visible as this enhancement on a CMH index. This enhancement is due to the compression of the magnetosphere, so through an additional is a booster on the geomagnetic field that gives this enhancement. So this is the very start, the very direction, so from a positive direction, as you see here, go very quickly, turn southward. So from a closed magnetosphere, we go towards an open magnetosphere. So I remind you from the first day again, that with an open magnetosphere, we can have the reconnection of the geomagnetic field with the interplanetary magnetic field happening from the nose of the magnetosphere, so in the sunward direction, and this gives the starting, the beginning of the main phase of the storm here. Then we have a northward turning of the IMF at that time. And you see that this time coincides with the peak of this first part of the storm. The negative peak is considered the end of the main phase, that is all this part of the behavior of the CMH. As you can see, we had a beginning just later on. We have a beginning of recovery phase, but again there was a southward turning of the interplanetary magnetic field coming from northward, so closed magnetosphere to open magnetosphere. That was a long-lasting event. You can see from 12 to 24 of the day of the 17th of March. So we are looking at about 12 hours of more or less constant southward IMF, so open magnetosphere, that give an addition of ionization, an addition of additional fields to the geomagnetic field in the opposite direction, so give rise to a decrease of the horizontal component geomagnetic field. So from an apparent recovery phase, we are now again seeing a decreasing of the horizontal component of the geomagnetic field, giving rise to an additional storm happening embedded in the first one that was that started here. So you see how complicated it can be. And finally, we have the recovery of the storm that happened when BZ comes to oscillate to around 0. So it was this turning of the southward towards 0 and oscillating around 0 nanotesla. And we have this low but regular recovery phase, so recovery to the quiet condition of the geomagnetic field. So you see from this stack plot how complicated it can be to have a clear picture of what is happening. What I would like to highlight and to let you notice is the displacement between what is observed in the BZ and what is actually seen at ground. You see that there are some kind of delay between the peak and the actual reaction of the geomagnetic field. This is due to the fact that these quantities are observed at the Lagrangian point, and we have then to account for the traveling time from the Lagrangian point to the ground. So let's go to see the reaction of the geomagnetic field from another paper, Nava and colleagues, 2016. The reaction of the geomagnetic field to the same storm, of course, looking at ground-based observation from magnetometers. You are seeing here as black line the component of the horizontal component of the geomagnetic field as observed by the magnetometer in Asia, top plot, Africa in the middle, and America. And you see in particular the location of the magnetometer in Vietnam, Senegal, and Colombia. And the quiet variation is identified with the blue curve that is called SHR. And the red curve account for the disturbances on the with respect to the quiet reference. So at first glance, you can appreciate the difference in the reaction, in the response of the geomagnetic field, looking at different regions of the world. Also the intensity, the severity of the variation of the geomagnetic field is different from a sector to another sector. So this is something that is we must to take into account to study the response of the ionosphere to the storm, because the response is also very strictly connected to the region that we are looking at. From the geomagnetic field, we are now looking at a couple of plots that account for the ionospheric response. So in this case, we are looking at regional and global assessment of the total electron content variation. On the top plot, you are seeing the regional variation. Maybe it's not very visible from your screen, but I can help you with the legend. The blue curve is the Asia sector. The orange curve accounts for Africa sector. Yellow curve is the American sector, and the Pacific sector. Sudden storm commencement and the peak of the geomagnetic storm as derived from the CMH indices. We can see how different are the reaction to the storm. For instance, you see that the variation of TC is decreasing in Asia for the second part of the interval that is highlighted, while in America and in the African sector, we have an increase of TC. So the response of the ionosphere is very, very different. And also during the recovery phase, you have a large displacement of TC in the different regions. The global behavior is a picture of the entire period that we are considering from all over the sector. And you are seeing here the two peaks of TC, the so-called positive ionospheric storm. So positive with respect to greater with respect to what is expected or what is predicted, what is the average behavior. This picture again from NAVA and co-authors, we see the evolution of the ionospheric equatorial anomaly. Maybe you remember that yesterday we described it quickly, but we described the existence of this variability of the electron density distribution over the equatorial latitudes due to the so-called fountain effect, due to the fact that there is a current system flowing in the E region of the ionosphere, flowing with a zonal direction that's combined with the horizontal direction of the geomagnetic field, give rise to an uplift of the F region electron concentration, and then with a fall down of the electrons that were uplifted. So this is the so-called equatorial, this is called a fountain effect that give rise to the equatorial anomaly. And the equatorial anomaly can be described looking at the days before the storm. Again, this reference time here is the sudden storm commencement. Sorry, before the storm, you can recognize the two crests of the fountain and the trough, so the minimum in between. And this is visible for all the sectors. Again, this stack plot look at Asian, African, and American sector. And when the storm begins, when the storm starts, you can see how much can be modified the anomaly, the Equatorial Anomaly. The most interesting feature is that the modification is very is strictly dependent on the local time sector. So in the different sector, the modification is completely the same. For instance, in the Asian sector, you have a very little modification, while the other two sectors, the Equatorial Anomaly is completely different at the starting of the storm. In particular, in the American sector, you cannot recognize the classical configuration that you expect during quiet time. I would like to draw your attention in particular on this modification of the storm happening in the Asian sector after the beginning of the geomagnetic storm, in which essentially almost you don't have anymore any anomaly. You have simply a weak enhancement, just a unique enhancement of the electron density concentration, little bit higher in the American sector. And then an evolution that see also an expansion and a shrinking of the crest extension, latitudinal extension, during the evolution of the storm. And these are the two sudden storm commencement, because we have seen that the storm try to recover at certain time and then again fall down. And we see how different can be the ionosphere according to the different region. Again, to see the evolution of the total electron density during the storm, this is another study by Zakharenkova and colleagues that see a global description of the electron density, the variation of the total electron density as blue and red color, because this identified negative or positive deviation from the reference frame, from the reference TC. And you can see in this sequence of picture that start from the 17th of March at 4 and with the 18th of March at 4 as well, so 24 hours, the evolution of the storm. In particular, you can see how the positive reaction, so the enhancement of electron ionization start from the North Pole and then expand all over the world. I would like to draw your attention on this particular frame in which we have this very, very wave-like description of the electron density variation, in which you can recognize stripes blue and red as alternate one to the other, and then slowly from a very big enhancement of in the negative and the positive phase, a slow recovery to the normal, to the reference condition. And also here you in the stack plot you can see the evolution of the Aurora Index, the AE index that we have seen the very first day, that remind you account for the auroral electrojet, so the current system that flow at high latitude, and give you also, in this case, the possibility to look at the evolution of the storm during time, along the time. And here in the stack plot, we have the response in terms of variation of total electron content in the European sector in this plot, in the North American sector, this plot, and in Central American sector. As you see, and as expected, the low latitudes, you see from the y-axis that here we are looking at the Equatorial Anomaly from a quiet state in which you can recognize the two crests. Then there is almost a lack of the Equatorial Anomaly, and then an intensification and expansion with the Equatorial Anomaly that go towards southern middle latitudes. So it was a very intense response of the ionosphere to this storm. I forgot to tell you that this TC is determined with respect to the TC 1 hour running mean. This is a paper that was co-authored by us, by our colleague Pasquali and us. And this is related to the response of the ionospheric sector over Southeast Asia. This is a reconstruction of TC along the time. We are looking from the 15th of March to the 26th of March 2015 as well. And again, you can see that in the day before the storm, you have, as expected, the two crests of the electron ionization visible here. And with the occurrence of the storm, the anomaly almost disappeared and the configuration completely changed, giving rise to this unique structure of enhanced ionization, weaker than, as you can see from the color bar, weaker than the crest happening just before the storm, and located around the geomagnetic equator. So not only we have a weakening of the ionization, not only we have a completely different configuration, which the crest almost disappeared. We can say that the crest disappeared in this case, but we have also a shrinking of the Equatorial Anomaly. This is confined in a narrow latitudinal sector. Then there is an expansion. You see, with respect to the previous day, an expansion of the crest. And then again, on the 22nd, during the recovery phase of the storm, we have another expansion of the Equatorial Anomaly. So, and this was taken from a network of receiver in the Southeast Asia, Indonesia, Vietnam, in particular, Philippines, yes. From the same paper, you are now seeing quite rich plots in which are reported different kind of information. First of all, there is the variation of TC, again, as in the previous paper that we have seen, as blue and red deviation from what we consider quiet condition. If I'm not wrong, Claudio, this was taken with respect to the most quiet days of that month. I remind you that the most quiet days are given by the World Data Center that provide also the indices, the geomagnetic indices. So you can rely on this kind of information source. And again, we are seeing from the 10th of March to the 26th. So we are following the evolution of the ionosphere before the storm, at the beginning of the storm, in the main phase, and at the recovery phase. These violet curves help us to follow the evolution of the storm because this is the DST index. So again, you are here in the almost quiet condition. Then there is the sudden commencement. Then there is the main phase of the storm with this shy recovery, but again, the main phase with the peak of the storm, then a recovery phase, but full of what we call substorm, that are storms embedded in the principal storms. You can see here the evolution of the Equatorial Anomaly again. You can recognize the crest, and then at a certain point with this, even before the storm because of these small storms, but what we care is to look at the beginning of the storm in which what you have as a result is a negative, big negative ionospheric storm. I mean that we observed a deviation from the quiet condition that times, and this negative storm lasts for some days for the bulk of the recovery phase of the storm, and then there is a recovery to the Equatorial Anomaly configuration typical of the quiet times. The black dots here are related to the appearance of scintillation on the amplitude of the signal. So you can see that before the storm, we have scintillation occurrence, while during the main phase and the beginning of the recovery phase, during this very big negative storm, we don't have any more scintillation. This is again quite typical of the low latitude ionosphere. This is called the suppression of small scale irregularities and inhibition of scintillations. And this is due to a sort of disappearance of the small scale irregularities that trigger scintillation. And you can see that there is again an occurrence of scintillation in this day, but again they disappear and they reappear after the recovery, at the end of the recovery of the storm. This is a similar exercise for what concerns TC, but in a different sector, in the African sector. This is a paper from Oluendo and other colleagues, among them also Claudio. This is the evolution again from the 15th of March to the 26th of March of the TC. And you can see that on the African sector, the bulk of the difference starts from the 1819 with the shrinking of the Equatorial Anomaly, essentially. And the other two plots at the bottom of these slides are related to the geomagnetic field as seen by a local magnetometer, in which we have, help me Claudio, the blue line and the red line, I cannot read.
It's two different magnetometer stations
okay.
In Africa. And by using these two magnetometer stations, we were able to estimate the equatorial electrojet. That is the blue line on the other plot that is strictly related to the morphology of the tests.
Perfect. Then there is another paper by Venkatesh and co-authors looking at the Brazilian sector. And here we see the TC on the 16 in red, sorry, in blue, and on the 17 of March in red. And so to compare the day before the beginning of the storm and the storm onset. And as you can see from the red line, the red dots, sorry, you can appreciate a positive, in this case, enhancement. So an enhancement of TC in the Brazilian sector. And this is the equator, I guess. Yes, it's the geographic equator. And how different can be the TC from one day, a quiet day, from another day that is the onset of the storm. And again, this CMH profile help you, and the KP profile help you to follow the evolution of the storm. This TC assessment has been done using this dense network in Brazil. From low latitude to high latitude, from this paper by Cherniak and co-authors, you can appreciate also the evolution of the auroral oval during the storm, the same storm, and how the convection cells are modified during the storms. This was the day before the storm, so 16th of March, and then you see the evolution. And in particular, I'll draw your attention on the 17th of March, in which you have a very, very big expansion of the auroral oval that is going towards middle latitude, and also the intensification of the rate of tech index, so of the variation, we can say, of the TC. Then on the 18th, you have a sudden shrinking and also a weakening of the intensification. And again, the configuration is almost the same of the day before on the 19th of March, but the intensification is higher. And slowly we recover to the condition we had in the previous day with respect to the beginning of the storm. This is of the, sorry, solar flare. Yes, this is another storm. This was of the from a very big storm that happened in the previous cycle of the October 2003, and for this late October 2003, and for this reason called the Halloween storm. This is a paper by Surutani and colleagues that let us see the reaction of the ionosphere, in particular of the TC, as you can see from the color bar here, of the TC to the occurrence of a flare at the subsolar point. So the subsolar point is, you can see, is the illuminated region in which you have an enhancement of TC that is very, to say, localized and very transient, because it happens in about 8 minutes from the solar flare occurrence on the sun, and it lasts for, I think, few minutes.
Yeah.
These are from some reference for your so if you want to go deeper, and of course among this list there are also the papers that I mentioned. So questions?
We had a question related to the previous part of the lesson. That is related to the intensity of the solar flare and the response of the ionosphere. I put a short reply on
the chat.
Okay. And Graciela had something more on the reply. And apparently no other question. This is a very important part of the lesson, guys, because this gives you an idea on how to exploit the data in order to understand the physics and the behavior of the ionosphere. So don't be shy and ask for questions.
So it's time for a break now.
Yeah.
So we will be back in 10 minutes.
So this last, let's say, half an hour will be dedicated to the way to get the data in order to analyze the ionospheric behavior during, for example, a geomagnetic storm. So I'm going to show you some of the most used databases and web portals from the ionospheric community in order to retrieve data for IMF, geomagnetic indices, ionospheric stuff, so basically TC and scintillation, and yeah, how to get the data, but also how to get the plots directly you can use to have a look to the data in order to understand what is going on. So the first one is database web portal made available by NASA. Is the CDA web. It is a very useful, very complex web portal, included several, let's say, hundreds of instruments, and especially satellites, instruments, and data collected by, acquired and collected and managed by the Americans. So what I would like to do with you is to try to navigate in a live session through the databases in order to show you how to get the data in a easy way, more or less, and in order to let you, to give you the possibility to analyze the data, to interpret the data, and to understand the ionospheric behavior. That is useful for the ones that is going to give the exam with us, but also for the others that are maybe curious of having a look to the data. So let's go to the CDA web portal. Let me try to show you the right. Yeah. So this is the home page from which you can select the instruments and satellites you are interested in. So in our case, for example, here we can retrieve the IMF data and some of the geomagnetic indices and solar wind parameter. So we can select this ACE satellite, and then the parameter we want to retrieve from the database. So we can select, for example, the activity indices and the, let me get the plasma and solar wind parameter here, magnetic field from space, and that's it. So clicking to submit, you will be redirected to the related pages. Here you can select a different data set from different instruments on board the same satellite. So we can select all the stuff, and we can select the Omni, for example. I can see very well. Mi puoi aiutare? Io vado là così leggo, se no non vedo. Okay. So we can select the yeah, it's Omni 5 minutes data. So this one that gives us the 5-minute IMF data and some plasma and solar wind parameters. So submit. Here we can select the date. So let's say during our St. Patrick Day storm. So something like 17 from midnight. Okay, to 17 to 18. Okay, and then you can select if you want to plot the data, to download the data in different format, and so on and so forth. So now we want to have a look to the plot. So let's submit the request. You can have a look on the metadata in order to missing variable selection. Okay, that's fine. Yeah, you're right. We have to select first of all the variable we want to retrieve. So in our case, for example, Vx, Vy, Vz, and then the velocity of the solar wind. So here, the temperature, maybe the Aurora Index, and the image that I recall you that is a kind of a DST. So submit. Okay, and we can get immediately the plot with the selected variables here. You can recognize maybe the DST with the sudden commencement, the main phase, the second CME arriving, and the recovery phase of the storm. So this is the first database, the first instrument you can use to get this kind of data. So basically the IMF and solar wind parameter, together with some, if you want, geomagnetic data, but I'm going to show you another repository from which you can get all the geomagnetic indices. For sure, if you are, let's say, able to analyze data by yourself, you can download the data and plot the data well, however you want. I mean, you can plot the data in a different way in order to match your needs. Then let's move to another one. So here we go. The next one will be the Kyoto World Data Center. That is the most famous data center for what concerns the geomagnetic data. The one that is in charge to calculate the KP and the other geomagnetic indices. So from here, we can, let me open the website. Okay, here we go. So from here, you can see the home page from which you can retrieve different kind of data, and in particular from here, let me check. Okay, let's do like this. It's AP. Yeah. Okay, for example, here we can have a look on the Aurora Index. Here we can select the month. I don't know, August 2021. And here on the left, we have the day. So they made available a daily plot of the Aurora indices. So you can have a look to the disturbances, if there are some. Just to recall you that we can consider the Aurora Index disturbed when it is more than 400 nanotesla in absolute value. So this Kyoto data center is a very useful one for the geomagnetic indices. For example, here we have the DST, and since a long time ago, So again, we can have a look. Okay, this is the validated data. So we have till 2014, but we have also the pages related to the real-time data. So this one. And we can select, for example, our St. Patrick Day storm. Here we go. Here you can recognize the DST. So we have the monthly plot of the DST. That is very useful to get the information about the DST disturbances during the geomagnetic storm. Let's move on. Let me. Okay, so now we have the instruments to get the data about the interplanetary magnetic field, solar wind, and geomagnetic indices. So let's move into the ionosphere. This Madrigal database is worldwide recognized database for what concern the ionospheric data, not only ionospheric, but for ionospheric data in particular. And this is very useful because through Madrigal, you can get global TC maps that includes data from thousands of GNSS receiver on ground. So this is a very useful instrument, even if this Madrigal is not so, let's say, friendly. So to use Madrigal, you have to spend some time to understand the functionality of the database. But basically, this is the homepage. You can access the data here by having a list of experiments included in the database or selecting a single experiment that is our choice. So here you can put your name. Okay, let's go with Lucilla. And your affiliation, so INGB. And you are here again. This is one of the bugs of the website, but it's like this. Okay, here you can select the instrument type. So we are interested in TC maps from ground-based GNSS receiver, so distributed ground-based satellite receiver. Then we can select the instruments, so the worldwide GNSS receiver network for TC and GNSS scintillation network for scintillation indices. Let's go for this one. You will be redirected to another, let's say, server. So again, your name. Okay. So now we can select the year. 2020, waiting for a bit, the month, let's say June, and the day. So let's say 16. Then here we have these worldwide TC maps for 16 or 17. Let's say 16 again. And then we can select the file. So we have different choice. This is the TC data, the SLAM TC data. If you remember what I said you yesterday, we have this TC calculated on the direction between the receiver and the satellite. But what I want to show you is the TC map 1 degree times 1 degree all over the world. So we can select here this TC map. And then download the files, view the information about the files, or plot the data. So here we can select TC maps for 15. I don't know why 15, but that's fine. And here you have the map every 20 minutes, or at the end, if I am not wrong, at the beginning. Okay, the animated GIF, including all the maps, and that's it. So you can see the evolution of the TC at the global level during one during one day, the day you selected, more or less. So from here, a lot of information can be retrieved about the evolution of the crest of the Equatorial Anomaly, about the auroral boundaries, about the large-scale TID, and so on and so forth. So here, for example, you can see the evolution of the Equatorial Anomaly moving, apparently moving westward during the day. And this is Madrigal, from which you can retrieve a huge amount of data. I mean, this is just an example of the TEC. You can retrieve scintillation data, but also other data from other instruments we had no time to describe for, I don't know, incoherent scatter radar, Doppler sounding, I don't know, maybe super DAR, other kind of instruments we had no time to describe you, but that are very useful to investigate the ionosphere. Let's move on. Okay, let's move to scintillation data. This is very important network of scintillation receiver located in Canada. So looking at the high latitude in the American sector, this is managed by Brunswick University there. And they have this very old-fashioned web portal, old-fashioned but very useful. So let's open the web page. I guess they are on the way to renew the portal. But okay, here you have the location of the maps and the last data available from each of the receiver, the location of the receiver, sorry. And you can do a lot of stuff here, but you have to register on the website. So you can register here with your email, and you will be able to go into the web portal. Here we can use, for example, the credential of our colleague Luca. Yep. So, for example, we can plot the GPS data, so the scintillation data. Here you have the list of the station available. All of them are in Canada. So let's say, I don't know, Eureka. So 2020, January, 1st of January, okay, and you have to select here, okay, let's say 24 hours of data. And here you can select the indices in which you want to retrieve. So let's say S4, the amplitude scintillation indices for all the satellite in view. Plot. And after a while, after some time, in few seconds. Almost there. Got it. So here you have the plots of the S4 index with respect to time, and with the different color for different satellite in view. And here a polar representation of the same data. So here you have on the center of this plot the station, and the distance, the radial distance from the center is the elevation of the satellite, and the direction here is the azimuth. So it's a way to give the coordinates of the pierce point with respect to the station, basically. And from here you can download the PDF of this plot. For sure, you can download the data, so you can plot the data whenever you want by using your own scripts. Here in chain website, you have also data from some ionosones. that are not ice, not the ionoson from Massachusetts, but there are CADI ionosons. Again, very old-fashioned ionosons, but very useful data here. So you can try to get also ionosons data from chain. Next one. Okay, this is the most beautiful one because it's from us. So this ESWA website is okay. We started this the development of this ESWA database more than 10 years ago, 12 years ago, something like this. But recently we completely renew the let's say back end of the system by organizing better the data in order to be able to make available the data in a easier way. And also we renew the front end, so the web portal. In this ESWA web portal, let me show you the home page. You have a lot of information in the home page. You have some gauge, some indication on what is going on in the ionosphere from a scintillation point of view, from a TC point of view, and from an HF communication point of view. So from the home page, you can get rapid information about the ionospheric behavior all over the world. And here you have some interesting real-time plot about the scintillation from the receiver we are directly managing all over the world, but we will see in detail. The last TC maps over Italy, and the last ionograms from Rome ionoson with the corresponding retrieved electron density profile. But this is only the web page. Here you have the HF systems web page, the scintillation, TC, and then some tools to compare the data and the data access and policy and the network description. So first of all, let me show you our network. So here you have this map from which you can, get the position of the GNSS receiver, GNSS scintillation receiver we are managing, the green dots, and the ionosons we are managing, so the red dots. We installed in these 2 weeks here in Argentina 2 different GNSS receivers, one in Ushuaia last week and one in Tucumán a couple of days ago. So they are the last entries on our database. And we have an ionoson here in Tucumán and one in Bahia Blanca, so 2 ionosons in Argentina. From all these receiver and instruments, you can get real-time and historical data. For example, if we want to retrieve scintillation data, we can select here the region, maybe South America. Let's go for the last data from Tucumán receiver. Okay, you can select an elevation masks to cut out the low elevation data that could be affected by multipath or error like this. And you have here a representation of the last 3 hours, if I am right, but you can select here the period, whatever you want. And here you have the location of the station, how many times ago we received the last data, so 6 minutes, because we are receiving data every 15 minutes. And here the satellites in view. And finally, the S4 and sigma phi indices from the receiver in Tucumán. Here you have the legend. You can select one single satellite or all the satellites, and you can download the data you are looking at, or download the image of the plot you are looking at. And here you have the TC from the receiver that is not calibrated. and the representation on the globe of the scintillation data. So quite complete representation of the scintillation data here. And you can select all the station, all the period you want, and so on and so forth. So moving to vertical sounding, so HF data. We have our ionosomes here. This is Roma ionosomes. The layout is quite the same, so the map and the latency of the data. And here we have some parameters. I have shown this kind of plots yesterday. Yep. So here you have a very quick look at the main parameters retrieved from the last ionograms recorded in Rome. So all the critical frequencies retrieved from the ionograms as a function of the time. And here you have the last ionograms recorded from the Roma ionosomes with the reconstructed ordinary and extraordinary traces and the electron density profile retrieved from the ionograms. And you can, again, get the data or get the images or do whatever. Okay, let's move to the last but not least database. Okay, here we have some example.
Graciana would like to start from.
Okay, sure. No, please. So so I leave the floor to our boss, please.
Thank you, guys. So what I'm going to talk about is monitor of the ionosphere in Argentina. So I will show you our portal, which is Tucumán Space Weather Center. That's a program from Universidad Nacional de Tucumán. This program is running with several collaborations. One of our main collaborations is with the INGV from, I don't know, 10 years or more. A lot of more years. So we have, okay, so you have monitoring the news and who we are mostly. And in monitoring, we have starting to put our main instrumentation. Currently, you will have all the information here in the web about our instrumentation, our instruments. So this is the INGV ionosome that already shown in the portal in Rome, but we have also here. And we are managing this instrument. We are managing also a Doppler continuous radar, Doppler radar, which is also in collaboration with Czech Republic in this case. And this is some explanation on the data so people can have a references how to use and how to see the data. We have a GPS receiver that now is going to be a GNSS receiver since just yesterday, I think. So during these 2 past weeks, as Claudio mentioned, INGV in collaboration with Tucumán and Servicio Meteorológico Nacional, we are working very hard. They have installed a GNSS receiver in Ushuaia and now one in Tucumán. And the data from both sides will be displayed here also. So we will be available. We have an old system also to work with. And we have a magnetometer and a radiometer. So we have a lot of instrumentation to work. But this is a beta version of our portal because we're working very hard. We have just two years working of this. The ionosome in Tucumán is going to be running today. It was in maintenance, and we are running also data from Bahía Blanca. You can see also the data here. You can choose how many days you want to plot, and there's a reference curve for You can choose the different reference curves to compare the data. So, for instance, there are, if you are choosing to see from the geomagnetic point of view of quiet tail, or you want to see more with another tendency with 27 average or some different statistics. So you can choose and work with that. We plot here all the last year ionograms. All the data is available, of course. Now it's available by sending us an email, and we prepare the data and send to you, or you can go and download it from the portal, but it will be easier I hope, in a few months. So this is the Doppler system. Now is not showing much because it's not working now, but it's something that also is in maintenance. And you can have here is the spectrograms. It will be, this is the last 3. And this is the new thing we are trying. I hope next week is going to be working. We are working in a database of TC for any of the station of Argentina. This will be a calibrated TC. So I think, okay, today we don't have it, but I think the next week is going to be there. Here is one of the main responsible of the work of the calibration, but the idea is to have all the data calibrated. We are working also in collaboration with Madrigal, so we have a global TC maps. Of course, we have the other condition, geomagnetic condition, and solar wind also from this escape index and so on. So in the few next years, month, I hope we have all the data and all our instruments here. So I think it's going to be a good and nice portal for Argentina, and we are working very hard to work in network with Argentina and in a regional point of view. So thank you. I think so.
Thank you, Graciela. Yeah, it's true. We are working very hard in a strict collaboration to improve the monitoring of the ionosphere.
Also forecasting.
And also forecasting. Yeah. But this is another story. So I guess we are at the end of our very brief flight over the most used databases for ionospheric for the ionospheric studies. So now what we suggest you is to try to get the data from this database and try to understand what was the ionospheric response to different geomagnetic storm. We are going to suggest by looking at the solar wind and IMF parameters, geomagnetic indices, TC response for the global maps, but if you want, also from a single station point of view, and then looking at the rate of change of TC or scintillation indices or rate of change of TC index to look at the scintillation from a scintillation point of view. So for the guys that are going to give the exam, just to say that we are going to send you an email with the indication of the geomagnetic storm we would like to we would like you study. And for the exam, you can prepare some slides in which you can, in 15 minutes, let's say, your results, your data analysis, but mainly your interpretation of the data. So we want to understand if you can get the crucial information by looking at the data. So this is the goal of the exam. For the other ones, it's just for fun. It's just for your curiosity, and for sure, We are available, me, Lucilla, but also Graciela, yes, for all the question you will for sure have in the next days, in the next period. So please don't hesitate to write to us, to ask question, to ask suggestion, and so on and so forth. So maybe Lucilla wants to add something.
Yes, for people that would like to take the exam, of course, in 15-minute slides, you cannot put everything. You have to choose what you want to interpret, what you want to show us. So it's also a matter of your taste, and also a matter of what you would like to highlight of a specific storm. In 15-minute slides, you have to choose. So this is part of your job for the exam, to be critical, to have a critical approach. So we do thank you a lot for your attendance, very active and also numerous. And I hope to be with you in touch in the next days, months, and be in touch with NGV, and I hope that this collaboration that is already very fruitful with Graciela and her team will grow up even more in the next months. So be in contact with us, and we will be happy to help and to exchange information and also discussion with you.
Yeah, so thank you also from my side. Thank you for being so active for a very long time, because yesterday we had this 3 hours lesson that was terrible. So thank you again, and I leave the word to the floor to Graciela to close the course.
First of all, I have to say thank you to both of you, because we make you work a lot listening this. Not only with the instrument, but also with the course, which I think it was very good. I like it a lot, and I think this is a good response from the students, a lot of interest. So I think it's a really good thing. Thank you to everyone here. And if you need anything from my side, just send me an email. I know in some university you will need further documentation or information if you want to do the formal certification and so on. So don't hesitate and contact me. I'm ready, and if you want to collaborate, for sure, we are very open to that. We like to work on this. We love to work on this kind of thing. So I think that's it. I don't know if any one of you wants to comment on something or say or ask some questions.
They are thanking us, all of us, and very nice and inspiring seminar classes. Many thanks for the initiative. Our inspiration was Graciela, indeed. So we thank Graciela for this opportunity, and all of you for attending, of course.
I will give like a heads up on next year, maybe, that we are trying to push curricula on space weather and ionosphere. So we are thinking about several other courses and machine learning courses applied to space weather. So stay tuned and contact, and we'll let you know as soon as we have more information. Thank you. Thank you very much.
Thank you very much. Where can we access the video?
Yes, I now as when we finish this session, I will compile everything and send you by email every information, the slides, the video, and the contact, of course.
And maybe last call for people that want to take the exam, to send an email to Dr.
Please
Molina.
send me an email, or Lucilla, of course, if you want to take the exam, someone is missing. So I think that's all.
Thank you.
Bravo.
Thank you. Bye. Bye.
Bye. Bye.